So LinkedIn recently made an upgrade in their tech stack. What they were able to achieve is something really interesting and worthy of a discussion. So we are going to take a deep dive into a case study where LinkedIn has managed to reduce the number of connections by 88% and latency by 75%. Now, this is a specific part of the setup, which is Espresso database, which is something in-house that they have built, and they use this as a primary database within. So what we will do is take a deep dive into this, go through the engineering blogs, try and understand what has happened and what led to this upgrade. This is really talking about two specific areas. One is database engineering, and the second is networking. So it's a combination of these two concepts, and that's essentially and effectively what has resulted in the outcome. So let's take a first take a deep dive into the summary of the problem. So this is their database. This is Espresso, and what this you can see that this is built on top of MySQL, but it's largely customized. There's two key areas. One is the router, and the second is the storage node. If you see over here, now storage node is made up of an API server and MySQL. Now, what happened in this, and then the other components are more of data replication, offline storage, and stuff like that. So we are largely concerned by this part of the system, and that's what the article also highlights, right? So what happened is when they added like 100 router nodes, it resulted in an extremely increased memory users in the storage node, as well as the latency also increased, right? And since they were doing a lot of connection pooling, and that was all HTTP 1.1 connections, the time to acquire the connection was really high, given the scale at which we're talking of databases. So it's really milliseconds level conversations that we're talking. And also when they were doing some networking events, something like upgrades, re-establishing number of connection due to errors, etc., this would efficiently or effectively take a large amount of time. Again, large is very relative in this conversation. So we are talking of really millisecond level and sub-second level conversations here. So you can go to the rest of the article. I'll try to hop on and highlight some of the articles that they have posted. And what they have done is they have taken Espresso, they have tried to customize a little bit of classes and upgrade it from HTTP 1.1 to 2. Now, what does this really mean and translate? Let's try and understand why is it that big of a thing, and why does a protocol upgrade, which is a transport layer upgrade, results in such a significant boost. And the whole article talks about the HTTP 1.1 2.2 implementation, how the pipeline works. I would highly recommend to go through this project, which is the Netty project. It's the networking framework that they use internally, and they have done a little bit of customization. So both of these are kind of ingrown. But let's hop on to the other part of the conversation, which is trying to understand HTTP 1 and 2. So imagine that you're trying to go to a restaurant. You're sitting in a restaurant, and there's just one waiter. So what happens is that waiter really has to go through each table, take a request, go, come back with a response, and do this. So you are creating multiple connections effectively, right? And that's not ideal. You're not performing at an optimal level. What HTTP 2 does is the same conversation can be done with one single TCP connection. So that's in essence what HTTP and 1 and 2 are about. Now there's more subtle differences, like HTTP 1 is more like text based and one connection at a time, and it can be boggled down by a large number of requests, and it's more like a walkie-talkie kind of an interface. So you press something, then the other person hears, and then you do that. But think of HTTP 2 as a smartphone with unlimited data, where which you're talking both ways. So that's what is happening. So you have multiple requests at the same time. You have binary based messages, which are really more efficient, and so that effectively results in a much better interaction between them. Let's take the same example or take the same image and try to look at a couple of different options. So this is what happens to the response time if you think about it, right? So if you just transpose the image, what we have looked here, and try and apply that to the response time, this is what happens. So if there's no queuing happening, you typically reduce the response time further. And if this is not clear, let's try and understand this with a slightly more zoomed out version of this. So if you look at HTTP1, you make an index call, you get a response. Then you ask for a style sheet, then you get a response. Then you go for a JavaScript request, and then you again get a response. And then the client renders the page and the connection is closed. Please remember the connection is closed. There's no, in order to, come back, again, a new connection has to be opened. So all the handshake, etc. needs to happen. Now, what happens in HTTP2, as you can see on the screen, is once you get the index initial response, you can really make multiple GET requests within that same time. So the time is really squeezed, the rendering is faster, and the connection remains open. So that's the inherent root cause that they ended up around, which is effectively that resulted in this problem and getting solved. If you see this, this is the kind of latency that they were looking at. This is in terms of time. So if you see the chart is it's fluxing at around 60 milliseconds. I think this is at millisecond level. And then it further after the migration, which they did sometime a year back, is, it's really bumped down to 20. So this is a really good upgrade from their standpoint. So that's what has been documented, and that's what was the core change about. So if you are working in an architecture now, it's important to understand how this applies to you. But before we do that, if you have not subscribed to my channel and have been listening so far, thank you, and please do subscribe. Now, when you design architectures, right, and when you are dealing with high volume applications where you have a large number of users, it's a typical web scenario. These kind of engineering problems really become critical. So your database designs, your server architecture designs, if they are communicating on older protocol, you will get stuck in similar kind of challenges. So if you see something like this happening in your setup, and essentially as you scale in more nodes and infrastructure, you see these kind of problem, do think about the network side of it and see if optimizations can be bought of it from that. All right, that was Akash from Cafe.io. Thank you guys for listening. Bye bye.